In this video, we will discuss the Diels-Alder reaction, which is an incredibly important reaction in synthesis because it generates six-membered rings. And as you might recall, six-membered rings are very common motifs in natural products, such as in steroids, which have the ABCD ring consisting of 3 six-membered rings. After this lesson, you'll be able to draw the mechanism of a Diels-Alder reaction, predict the products of a Diels-Alder reaction, including stereochemistry and regiochemistry. Regiochemistry just means two parts of the molecule might react, resulting in two different constitutional isomers, but only one is observed. Finally, you'll predict the relative rates of Diels-Alder reactions based on molecular orbital theory and conformational analysis. Ooh, fun. As I mentioned, the Diels-Alder reaction is one of the most significant reactions in organic synthesis. And again, that's because it generates this six-membered ring. Let's start by drawing the curved arrows for this reaction, labeling the functional groups, and thinking about how you'll recognize an example of a Diels-Alder reaction. The Diels-Alder reaction is a concerted reaction, meaning that all of the bonds that are made and broken are made and broken at the same time in one single transition state. We can see that these two new sigma bonds are made between a diene, and those four atoms end up right here, and what is called a dienophile. That's just fancy for alkene, right? Well, it's an alkene with an electron withdrawing group on it. This ester group represents an electron withdrawing group. Pi bond adjacent to a pi bond. You can push the electrons up into it, so it's a pi electron withdrawing group. And this whole species is called a dienophile. It likes dienes. It reacts with dienes. Let's draw the curved arrows for this transformation now. The diene donates pi electrons to the dienophile. That will break this pi bond. So those pi electrons react with the other end of the pi system of the diene, pushing these electrons over. These pi electrons make the sigma bond between what I've arbitrarily numbered as carbons 4 and 5. These pi electrons from the dienophile form the second sigma bond that's made. And these pi electrons, the other pi electrons from the diene, they make a pi bond here. The diene and the dienophile combine to generate a cyclohexene. And that is how you will recognize the Diels-Alder reaction. You will recognize it because you will identify a cyclohexene functional group in the product. If you are wondering, what is that triangle? Well, that's delta, and it means heat. That means thermal energy is facilitating this transformation, and we'll talk more about that in a bit. Let's take one more look at this concerted transition state, this concerted mechanism for the Diels-Alder reaction. We can see the electrons are moving in a circle. So this is an example, the Diels-Alder reaction is an example of a pericyclic reaction. In pericyclic reactions, electrons flow in a ring or in a circle. Now that we know that diene plus dienophile gives a cyclohexene, when we know the curved arrows for this transformation, let us try our hand at it. So pause, draw the curved arrows for and the products of each of these Diels-Alder reactions. Give it a shot. Keeping in mind the generic arrows for the Diels-Alder reaction, we will propose mechanisms for each of the reactions below. This diene with this dienophile, aka fancy alkene, react in the following manner. The diene attacks the dienophile, and those pi electrons make another sigma bond with the diene. Then the final pi electrons in the diene slide over and make that pi bond in the cyclohexene product. Now in the second reaction, you may have noticed that these are the same reactants that we have already discussed. This diene, however, will undergo bond rotation around the sigma bond to access what is called the S-cis conformation. You may recall our discussions of dienes from our first unit of the course. And although the S-trans conformation is the more stable conformation of these two, the S-cis conformation is the one that the molecule reacts in. Does it matter that the S-cis conformation is less stable than the S-trans? No, it does not. Once the molecule's in the S-cis, it can react. Of course, the rate of the Diels-Alder reaction does depend partially on how much the molecule is in the S-cis conformation, and we'll certainly discuss that as we continue thinking about the Diels-Alder reaction. But just because this is the minor conformation doesn't mean the reaction doesn't occur. It does. So once the diene is in the S-cis conformation, here showing it in a plane perpendicular to the page, the dienophile can approach the diene either from the top side of the diene or from the bottom face of the diene. But again, these bonds are formed at the same time. Approach from the bottom or the top face of the diene does result in a racemic mixture of the product. It's not necessary to draw out both enantiomers. We can simply indicate that it is a racemic mixture the way that we did here in the previous slide, right? We just said plus minus. So that indicates that this product is formed as a racemic mixture. I just wanted to show you that that racemic mixture results from attack to both the top and the bottom face of the diene. Good work. It's important to let you know that the Diels-Alder reaction is a reversible reaction, meaning that it proceeds in the forward and reverse directions. Please draw a complete curved arrow mechanism for the retro Diels-Alder, the reverse Diels-Alder, as shown below. And then consider this question. What direction of the Diels-Alder, forward or reverse, so forward or reverse, is favored by delta H and delta S? Give it a shot. In the forward direction, you will recognize the Diels-Alder by the cyclohexene in the product. In the reverse direction, a cyclohexene decomposes to generate a diene in a dienophile. In the forward direction, a ring is made. Acyclic starting materials generate a cyclic product. In the retro Diels-Alder, a cyclic starting material generates acyclic products. Once you've identified that a retro Diels-Alder is occurring, you should be able to draw the curved arrows. It might be most useful to start from the pi bond and the cyclohexene. The carbon atoms on either side of that pi bond will be part of the diene. These bonds will be broken. The electrons in the pi bond scoot over. They're going to reform that pi bond between carbons 1 and 2 in the diene. Generation of that pi bond between carbons 1 and 2 breaks the sigma bond that is made in the forward direction. So these electrons between what I'll just arbitrarily call carbons 1 and 6, they reform that pi bond between carbons 6 and 5, breaking the sigma bond. And this is also a concerted mechanism here. So when this pi bond is formed, that breaks the sigma bond between carbons 4 and 5. Those electrons now will reform the pi bond between carbons 3 and 4, breaking that sigma bond. So these arrows are the opposite of the arrows from the Diels-Alder in the forward direction. That's what it means to be a reverse reaction, right? The arrows that show the reverse direction of the reaction should be the exact opposite of those that show the forward direction. Now, thinking about what direction that the Diels-Alder is favored by delta H and delta S, let's first remind ourselves of what those two terms refer to. Delta H refers to bond strength and delta S refers to entropy, and together they influence delta G, whether or not it is positive or negative. Recalling that negative delta G is favorable. Considering the forward direction first, 3 pi bonds are broken in the starting material, but 2 sigma bonds and 1 pi bond are formed in the product. The reverse direction would of course be the opposite. 2 sigma bonds and 1 pi bond are broken, while 3 pi bonds are made in the product. Because sigma C bonds are stronger than pi bonds, in fact, the forward direction is favored by delta H. On the other hand, in the reverse direction, one molecule, is converted to two things, two molecules. The two things represent more degrees of freedom than one. Thus, in tropic term, delta S does favor the reverse direction. Recall the expression for the Gibbs free energy, which favors a spontaneous reaction when delta G is negative. The enthalpy term, delta H, is most significant at low temperature, whereas delta S predominates at high temperature, since temperature is a factor in that delta S term. Now, what the exact temperature is that changes the predominant factor from delta H to delta S, that varies from reaction to reaction. And obviously, we're not going to think too much about that, worry too much about that. We just want to be sure that we understand the forward direction is favored by delta H, the reverse direction is favored by delta S, and both of these reactions, reverse and forward, will be observed by you as an Organic Chemistry 2 student and as an advanced practitioner of organic chemistry in your continued studies. And if you are concerned that there is heat in both terms and thinking about how that relates to temperature, that concern is definitely valid. These reactions are often heated, so it does refer to temperature, but the delta here is, again, referring to thermal energy, and it's just a bit different than just brute heat to make a reaction occur. So we're going to talk more about what this delta means as we move along. But don't be too concerned about, there's delta, there's heat and temperature, so it's always going to favor the reverse. That's just not true. And you're not going to have to predict too often which direction is favored. I'm going to give you, okay, draw this mechanism or predict the products of this reaction. So you won't be having to make many decisions about which direction is favored. You just need to know that both directions of the reaction can occur. We will change gears just a bit and consider this transformation. Do you think that this is an example of a Diels-Alder reaction? So the first thing that you might do is just classify or describe what a Diels-Alder reaction is. Write down your description. Think about this example and consider whether or not it fits that description. Give it a shot. I've written a possible description of the Diels-Alder reaction based on what we have already discussed here at the top of the screen. Looking at this example below, it looks similar and different. Helpful, right? Well, we have an alkene, so we can imagine that this could perhaps be a dienophile. It could like dienes. And this species looks a bit like a diene, except it's not. It's an alpha beta unsaturated aldehyde. But it does represent a 4-atom, just like for the diene, 4-atom, 4-pi electron system. So in that way, it's similar to a diene. And we could draw curved arrows for this process. We'll form this bond. Pi electrons scoot over, use these pi electrons to form that bond. In fact, those are the two bonds that are formed. We can number the atoms the same way that we did for the Diels-Alder on the previous slides. So the curved arrows look pretty similar. The same idea that there's two sigma bonds that are formed. These two sigma bonds are formed, one pi bond formed, and then in the starting material, 3 pi bonds are broken. So this reaction certainly looks similar to the prototypical Diels-Alder that we have been discussing. There are a few differences. One of those differences is that the dienophile has an electron withdrawing group, whereas the potential dienophile in this reaction, it has an electron donating group. That makes the dienophile in the normal prototypical Diels-Alder reaction, that makes it the electron poor species. And the diene is typically considered electron rich. Often it will have electron donating groups on it. We saw that in this example here. So this diene had an alkyl group on it. And we know alkyl groups are electron donating groups. We'll see that's oftentimes the case for the quote-unquote normal or typical Diels-Alder, that the diene is the electron-rich species. And this is basically opposite for this reaction down here that we're considering. The dienophile is electron-rich. It is probably acting as a nucleophilic species. It's electron-rich. And the diene-like species is electron-poor. It's off-beta unsaturated aldehyde. We know that those are electrophiles. But ultimately, there are 6 pi electrons reacting in this circle. We have a 4 pi electron piece coming together with a 2 pi electron piece in the same exact way as for the Diels-Alder. So in fact, this reaction is considered a Diels-Alder, but because the electronics are switched, the dienophile is electron rich rather than electron poor. This reaction is referred to as a reverse electron demand Diels-Alder, or the dienophile is electron rich instead of electron poor as in the prototypical Diels-Alder. We have achieved now one of the learning goals for today's lesson, which is to draw the mechanism of the Diels-Alder reaction. And perhaps we should add forward and reverse direction. To be sure that we have achieved this learning goal, let's draw the curved arrows for these 2 reactions. Here is a Diels-Alder in the forward direction, followed by a Diels-Alder in the reverse direction, which is known as a retro Diels-Alder. Pause and try to draw the curved arrows. If you'd like, we can imagine rotating around the carbon 2,3 bond to generate the reactive conformation of this diene. We can then draw the curved arrows. These 2 bonds are formed. Now, if some of you are probably wondering, so could I have drawn the arrows in the opposite direction? So like this instead. I will accept that answer, but I am drawing the arrows the way I am intentionally, and I will explain that later on. But for now, either way is okay. Excellent. I did want to draw out the nitro groups just to be absolutely sure that we remember they are electron withdrawing groups. We recognize that because there is a pi bond adjacent to a pi bond. And so we can push the electrons from the dienophile up into the nitro group. And then we can really see how that nitro group is withdrawing electrons from the double bond. And we can do that in both nitro groups. And you can try to draw that out yourself, and you should. Same idea for the nitrile. There's a pi bond adjacent to the alkene, and we can show how that pi system results in delocalization of the electrons into the nitrile group, withdrawing from the 2 carbons of the alkene that we consider an alkene. Of course, really, it's conjugated pi system. I just wanted to be sure we remembered how those are electron withdrawing groups. We've drawn the curved arrows for this first reaction. Let's go ahead and draw curved arrows for the retro. Give it a shot. I made it a little more complicated, but you have the product, so you can definitely handle this. Use the pi bond in the cyclohexene. So it's this cyclohexene that we're considering here, and I know that, I can tell that because of the electron withdrawing group. So the electron withdrawing group is going to be bonded most often to the dienophile. And then use the pi bond and the cyclohexene as your anchor. You know that the carbons adjacent to it will be part of the diene. So these carbons are part of the diene. Now we know that those bonds in pink were formed, so we need to break them. So we're going to slide over these electrons. Slide them over, make the pi bond here. We've made those 2 pi bonds. And then the electrons in this bond are going to move over as well. And that looks like this to generate that pi bond. We just double check that in fact a diene and a dienophile were generated and everything makes sense, and then we feel pretty good about it. Well, now that we can draw the curved arrow mechanism for the Diels-Alder reaction in the forward and the reverse direction, and we're a bit familiar with the types of molecules that undergo this transformation, We want to really dive in now. We're going to think about the diene, we're going to think about the dienophile in a bit more detail and how it affects the stereochemistry and regiochemistry constitutional isomer of the product. And we will start with the diene. I have alluded to conformational analysis of dienes a few times today, but now I'd like to review this question from many, many lessons ago. Conformational analysis of the rotation around the single bond in 1,3-butadiene shows that it has two stable conformations, both of which are planar or nearly planar. I want to think about why these conformations are particularly stable and which one is more stable and why. Please write down your answer to this question and then we will compare and think about how it applies to the Diels-Alder reaction. The two particularly stable conformations of 1,3-butadiene are known as the S-trans and S-cis conformations and can be interconverted by bond rotation around the carbon 2,3 bond. We, of course, know that this is actually a conjugated pi system. Butadiene is actually a conjugated pi system. And that there's even some double bond character between carbons 2 and 3 because they're involved in the conjugated pi system that spans all four atoms. However, in the most stable resonance structure for this molecule, in the structure the way that we draw the Lewis structure, the skeletal structure for this molecule, the carbon 2,3 bond is represented as a single bond, even though we know, because it's a conjugated pi system, that the 2,3 bond does have some double bond character. It's shorter and stronger than a typical single bond. It's drawn like a single bond, so it's drawn like a sigma bond, sigma single. So S trans and S cis, those names come from the fact that the two conformations are interconverted by rotating around what is drawn as a single bond. Both of these conformations are planar or nearly planar. Can represent the S-trans conformation like this, where all four of those carbon atoms are in the same plane, which I'm trying to represent perpendicular to the plane of the Bohr. That means that the p orbitals are in the plane of the Bohr. And of course, the hydrogen atoms that are implied on each of these carbons, they're also in that plane perpendicular to the page. But the p orbitals here are what is most important. If this molecule is perfectly planar, then the p orbitals are all aligned and parallel, and that allows for conjugation between all four of the atoms in the system. Whereas the S-trans conformation is perfectly planar, the S-cis conformation is not. Ideally, it would be because that would allow for all four of these p orbitals to perfectly align, just as they did in the case of the S-trans conformation. However, keeping in mind that all of those implied hydrogens are in the same plane as the carbon atoms, since each of these carbon atoms is sp2 hybridized, having trigonal planar geometry. The two hydrogen atoms were on carbons 1 and 4 that are pointed into the center of the molecule here, into the middle of the molecule. If the entire system is perfectly planar, then the electron clouds of these two hydrogens are clashing. And though the fully planar conformation would be ideal for the conjugation of these four p orbitals, unfortunately, the energetic penalty of this steric clash outweighs that and causes the molecule to skew a little bit. What that means is that there's some rotation where one of these hydrogen atoms will move slightly up and one of these will be moved slightly down. So the molecule will be nearly planar, but not entirely planar. I'll show you that with the models. But because the molecule is nearly planar, not entirely planar, it's not fully conjugated or doesn't benefit from full conjugation. So it's just slightly higher energy than the S-trans. Let's take a look with the models.
This is the S-trans conformations, carbon 1, 2, 3, 4. Fully planar conformation. The p orbitals are perpendicular to the plane occupied by the atoms, parallel with the screen. The plane of the atoms is perpendicular to the plane of the screen. Now, rotation around the carbon 2-3 bond like this generates the S-cis. You can see in the S-cis conformation, these two hydrogens pointed into the middle of the diene. Their electron clouds would clash, so the molecule rotates just a little bit so they don't clash. But now this is not fully planar. The atoms do not fully occupy the same plane, so the p orbitals will not be fully parallel and aligned, and thus this conformation is slightly higher energy than the S-trans that is fully planar.
Summary. These are the two lowest energy conformations of a 1,3 diene. And the molecule, as long as there's free rotation around the 2,3 bond, is rapidly interconverting between these two conformations. Even though the S-cis conformation is higher energy, this is the reactive conformation in the Diels-Alder. So if we wanted to think about a question such as this one, rank these dienes from fastest to slowest rate of Diels-Alder reaction, we do need to consider, well, how often or how much will these dienes occupy the S-cis conformation. And for those dienes that have flexibility, meaning free rotation around the 2,3 bond, the distribution into the S-cis is largely governed by the magnitude of this steric clash. Imagine that there were alkyl groups instead of hydrogen. Yikes, the S-cis conformation would be even higher energy and less occupied than it is for 1,3-beta diene. For these examples, however, there is not free rotation around the carbon 2,3 bonds. These dienes are locked because they're involved in some cyclic system. So keeping in mind that dienes react in their S-cis conformations in the Diels-Alder reaction, please take a moment and rank these dienes from fastest to slowest rate of Diels-Alder reaction. Molecules A and B are locked in the S-trans conformations. Thus, they will have the slowest / no reactivity in the Diels-Alder reaction. On the other hand, molecules C, D, and E are locked in the S-cis conformation. Therefore, they will undergo Diels-Alder reaction. In fact, we might predict that molecule C is the fastest, followed by D, and finally E. Why might one predict that? Great question. Let's look at the slowest one first because I think it's the most confusing. One might say, hey, look, there's an electron donating group on this diene. That should speed up the rate of Diels-Alder. Just, just guessing, given our initial analysis. Or I did mention often the diene in the normal electron demand, often the diene has an electron donating group and the dienophile has electron withdrawing groups, such as represented here at the top of the screen. And although the oxygen is an electron withdrawing group, this molecule furan is aromatic. So although it does undergo Diels-Alder reaction, the product of the Diels-Alder reaction between, say, it and acrylonitrile, dienophile we've seen a couple of times, that Diels-Alder reaction will produce a non-aromatic product. What? Diels-Alder? Yes, Diels-Alder, here's the cyclohexene, and then the oxygen, just a substituent off of the two carbons of the diene. It is still there. So a bird's eye view of this molecule would look like this. It's a bicyclic system. So again, here is the cyclohexene. I will think more about these bicyclic products later, do not worry. My point is, it is no longer aromatic. So actually, E undergoes a slow Diels-Alder reaction and it loses aromaticity in the process. For D versus C, well, we can just think about the groups on the ends of the diene. So for C, there are these hydrogen atoms, whereas for D, there are CH2 groups. And you can imagine for the CH2 groups, when a dienophile approaches from either the top or bottom face of this molecule, it will encounter those CH2 groups. It will encounter their electron clouds, and that might slow down its approach. Meanwhile, for C, this entire end of the molecule is flat, and when a dienophile approaches for the top of the bottom face, there will be no hindrance to its approach by, say, these pesky hydrogen atoms sticking up or down in the path of the approach of the dienophile. We will look at some more examples, but first, let's just take a moment and really try to explain why the diene in the Diels-Alder must react through the S-cis conformation and not the S-trans. I've said that's the case, but why? Well, recall the mechanism. Both bonds, both of the sigma bonds that are made in the product, they are formed at the same time in this concerted fashion. Only a diene in the S-cis conformation will allow for this concerted reaction to happen. I always love drawing out the 3D transition state. Both ends of the diene must make bonds to both carbons of the dienophile at the same time. That's just not possible in the S-trans conformation. Carbon 1 may be able to reach, but carbon 4 is not close enough in space to make that bond. It's not close enough. Now that we've clearly articulated why the diene in the Diels-Alder reaction must react through the S-cis conformation, let's move on to these acyclic dienes. Rank these dienes from fastest to slowest rates of Diels-Alder reaction. This question is a bit harder than the first one because in this question, everything was locked. That is not the case here. So for these molecules, I highly suggest that you draw them in the S-cis conformation first before answering the question. Give it a shot. We must first imagine rotating around the carbon 2,3 bond in the diene to convert these molecules from the unreactive S-trans conformation to the reactive S-cis conformation. Students often find this to be a difficult exercise, but what I suggest to you is that you look at each double bond and what its conformation is. So this is a trans double bond. It is going to remain a trans double bond in the S-cis conformation. Oof. Yeah, the S-cis part, it really is just referring to carbons 2 and 3, right? S-cis. It's this fake cis and trans thing. I say fake because there's free rotation, free-ish rotation around that 2-3 bond, but there is not free rotation around the carbons 1-2 or the carbons 3-4 bonds because those have much more pi character. They're drawn as double bonds for a reason. So what I'm labeling in pink here, cis and trans, it is referring to the double bond, the alkene geometry. So carbons 1 and 2 or 3 and 4. Trans, about 3, 4 in the first molecule. Cis, about 3 and 4 in the second molecule. Cis, about 3 and 4. And then also we have to look at carbons 1 and 2, cis. There's a lot of usage of cis and trans happening here. All right, so in the S-cis conformations, all of these dienes will look like this, where this S-cis and S-trans, again, is referring to rotation around the single bond, the carbon 2-3 bond, because there's free rotation. And again, that is not the case for the bonds that are represented better by more double bond character, like carbons 1-2 and 3-4. All right, so 1-2 is all set in this first molecule. Let's label these. Let's go G, H, and I. There's a methyl group on carbon 4 and G, and the carbon 3-4 bond is trans, so that methyl group would be here, preserving that trans stereochemistry about carbons 3 and 4. All right, for H, carbon 4 should have a methyl group, cis, so the methyl group would go right there. We can see that cis relationship between the two non-carbon substituents on carbons 3 and 4 of the alkene. So there's the unplay hydrogens. I'm going to erase them. Cool. Now for molecule I, carbons 3 and 4 are cis, so there is the methyl group. Carbons 1, 2 is cis, there's the other methyl group. Ah, yikes, quite a steric clash. Well, this unstable steric interaction certainly makes this S-cis conformation for I the highest energy. Thus, molecule I will have the lowest percentage of molecules occupying the S-cis conformation relative to molecules G and H. Thus, I will undergo Diels-Alder with the slowest rate. Molecule H has a similar but not quite as bad steric interaction between the methyl group on carbon 4 and the hydrogen on carbon 1. And of course, these are just arbitrary numbers. They're not nomenclature numbers. All right, so there we have a steric interaction. It's not quite as bad as for I, where it's two methyl groups interacting, but it is still high energy and much higher energy than the two hydrogens that are in the middle in molecule G. Diene G will react the fastest in the Diels-Alder reaction, followed by H and followed by I. We should revisit the learning goals. We've drawn the mechanism of a Diels-Alder reaction, and we're working on predicting the relative rates of Diels-Alder reactions based on conformational analysis. So we've learned that more diene molecules in the S-cis conformation means a faster rate of Diels-Alder. For example, a molecule with a diene locked into the S-cis conformation would be have the fastest rate of Diels-Alder, versus an acyclic diene where there's free rotation. It is not locked, but there's just normal steric interactions between the hydrogens that are pointed in the middle. Faster than a diene that has a methyl group pointing into the middle of it when it is in its S-cis conformation. So this would certainly be slow. And then the slowest would be if the diene is locked in the S-trans, because this doesn't have any chance, zero chance of accessing the S-cis conformation and reacting in the Diels-Alder. We will discuss electronics later. However, we did learn that furan would react slower than the equivalent non-aromatic molecule, since the Diels-Alder reaction would break the aromaticity in the furan. Let's move on to predicting the products of the Diels-Alder reaction, continuing our exploration of the two parts of the Diels-Alder, the diene and the dienophile. Pause and predict the major product of each of these Diels-Alder reactions. You can draw curved arrows as well. All right, last chance to pause. In these two reactions, the same diene, which you will notice has an electron donating group on it, which is consistent with the diene acting as the electron-rich species in normal Diels-Alder reactions, and the dienophile acting as the electron-poor species in normal Diels-Alder reactions. Speaking of the dienophile, these dienophiles are similar but different. There is the cis stereoisomer and the trans stereoisomer of this dienophile. And in fact, these two reactions do yield different products. Reaction of the cis alkene yields the syn Diels-Alder product, where the electron withdrawing groups in the product cyclohexene are syn to one another, meaning on the same face of the ring. This product is formed as a racemic mixture, as indicated by plus minus. It is a 50-50 mixture of two enantiomers. However, it is one single diastereomer. In other words, there is no product that has the nitriles anti to one another. In fact, that product is the single major organic product of the Diels-Alder reaction between the trans dienophile and that same diene. Each of these products is a single diastereomer and depends on the diastereomer of dienophile that is used. This is an example of what is called a stereospecific reaction. Different stereoisomers of the reactant lead to different stereoisomers of the product. The fact that a racemic mixture of the Diels-Alder adduct is made just comes from attack to the top and bottom face of the diene. And that's normal. When achiral starting materials make chiral products, they are formed as racemic mixtures. The important stereochemical aspect of this reaction, the stereospecificity that I am referring to, is that the cis alkene, the cis dienophile, gives exclusively the syn diastereoisomer of product as racemic mixture, that's fine. And the trans dienophile gives specifically, selectively, the anti-diastereomer of product. So the stereochemistry of the dienophile is preserved in the Diels-Alder reaction. And now it's your try. Predict the products of this Diels-Alder reaction and include stereochemistry. The same diene as in the previous example is treated with a different dienophile. It still has an alkene. There are still electron withdrawing groups on the alkene. It's just that the electron withdrawing groups are connected. It's an anhydride. They have the electron withdrawing groups on the two carbons of the alkene have a cis relationship to one another because they're connected. Nevertheless, this is a cis stereoisomer of a dienophile. Just a bit funny again because the electron withdrawing groups are actually connected. The Diels-Alder reaction will proceed as always. So these pi electrons will make a sigma bond between carbons 1 and 6. The pi electrons between 6 and 5 will make a sigma bond between 5 and 4. And then the 3, 4 pi electrons move over between carbons 2 and 3 to generate a cyclohexene. If you're feeling nervous, just put in the numbering and then draw the substituents that should be at each carbon. Now 6 and 5 have become stereocenters, and the two electron withdrawing groups will be on the same side of the cyclohexene. They'll be syn, since they were syn in the starting dienophile. All right, so this is a racemic mixture. I do want to point out just one thing here, one additional thing, which is that these carbonyl carbons are sp2 carbons. The tetrahedral annotation here is referring to the sp3 carbons, so it's referring to the new stereocenters. However, some chemists don't like to show dashes and wedges that end at sp2 carbons since sp2 carbons are flat, they're trigonoplanar. So you might see this molecule represented where just the stereocenter to hydrogen is shown. And that means that the stereocenter to the carbonyl carbons, the sp2 carbons, or that bond is implied. The hydrogens might be shown because showing a wedge here is kind of ugly since the wedge connects to an sp2 carbon, right? This is an sp2 carbon. sp2 carbons are trigonoplanar. So again, some chemists don't like to draw dashes and wedges to sp2 carbons, but having the hydrogens down like this implies that the other bond is up. So it implies that these bonds are out of the plane, as I've shown in the other drawing. Okay, so these two drawings are equivalent. And if you see either convention, you will be fine with it. The bottom line here is that a racemic mixture of the syn isomer of the product is observed since the cis dienophile was used. Syn product because, again, the two electron withdrawing groups, they're both up. Syn. Good work. Now let's explain why. Let's explain why the stereochemistry of the dienophile is preserved in the Diels-Alder reaction. In other words, why does this reaction lead exclusively to the syn product from the cis dienophile and not the anti? The anti is not observed. Let's explain it based on the transition state. Give it a whirl. The formation of these two bonds in a concerted fashion, meaning that the bond on this end of the molecule is made at the same time as the other end of the molecule, does not allow for any bond rotation to occur around this pi bond in the dienophile. Thus, the stereochemical relationship in the dienophile, in this case cis, is preserved in the product and remains syn. The only way that these two groups could become anti to one another is if there were bond rotation. That could happen once this pi bond breaks and the electrons are donated. However, there is no time for that because at the same time, the other carbon-carbon bond is forming. This is a concerted reaction. All the bonds are made and broken at the same time. Now that we have considered how the dienophile stereochemistry affects the stereochemistry of the product, let's move on to think about the diene. For some substituted dienes, stereocenters will result. We've already seen that for dienophiles, those carbon atoms may become stereocenters if they bear an electron withdrawing group and if the cyclohexene is chiral. So for which carbons of the diene is this the case? Which carbons of the diene may result in stereocenters if the diene is substituted on those positions? There are 4 dienes here for you to use to consider this question. I would suggest that you just consider the simplest Diels-Alder with ethylene. Draw the products that would result and think about what the patterns are for which carbons of the diene, when they're substituted, may result in some stereocenter in the product. Well, oops, dienes A and B are the same. I made a note to change that last time I taught this class, but I forgot. All right, drawing the curved arrows for the Diels-Alder reactions for dienes A and B, which are the same, yields a product that looks like this. We can see that when there is a substituent rather at carbon 4, a stereocenter may result. Carbon 4, carbon 1, that numbering is arbitrary, right? However, for carbon 2, that remains sp2 hybridized and does not generate a stereocenter, even though there was a substituent on carbon 2. So I bet that's going to be the same case for diene C that has substituents on carbons 2 and 3. Those carbons will remain sp2 hybridized in the resulting cyclohexane product, and so they will not bear stereocenters. And that is, in fact, the case. Okay, for D, carbons 1 and 4 contain a substituent. In this case, though, that substituent is the same. So there is actually a plane of symmetry through this molecule, but we can see that if they were different, so if they were 2 different substituents, or if there was anything else, if there's another substituent or there's electron withdrawing group, then there would not be a plane of symmetry here. But for the molecule given, there is a plane of symmetry. So this would actually be a chiral, this particular molecule. But overall, what we see is when the diene has a substituent on either C1 or C4, a stereocenter can result. Carbons 2 and 3, on the other hand, do remain sp2 hybridized and thus cannot represent stereocenters. Well, now that we know that stereocenters can result from the carbons that come from the diene, let's give it a shot predicting the products of each of these Diels-Alder reactions. And what you'll notice is that both the dienophile and the diene have substituents on the carbons, making the new sigma bonds, so stereocenters may result. All right, predict. Once you have made these predictions, let's compare to what is observed. Given the observed products below, what can you say about the relationship between the stereochemistry in the diene and the stereochemistry and the product? We should be all relatively comfortable thinking about the stereochemistry of the dienophile and how that relates to the stereochemistry of the product. The trans-dienophile is expected to have an anti-relationship between the electron withdrawing groups in the product, and that is indeed the case. We can assume that diene stereochemistry does affect the product as well, but it might be harder for us to think about how and what the patterns are, which is the point of this slide. Well, we can see in the first example that the methyl groups from carbons 1 and 4, keeping in mind that carbons 1 and 4 are the carbons that could become stereocenters in the product, and indeed that is the case here. This product has 4 stereocenters and is formed as a racemic mixture of the single stereoisomer, the single diastereoisomer. The methyl groups on carbons 1 and 4 end up syn to one another in the product. So right now we're thinking about two relationships. The relationship between the substituents in the diene, like what is their relationship to each other in the starting material and the product. And then separately from that, the electron withdrawing groups, what are their relationships to each other? So we're not at this point thinking about how the substituents on the diene relate to the dienophile. We'll get there, but we're just thinking about how the substituents on the diene relate to themselves, and then how the substituents on the dienophile relate to each other as well in the product. Now looking down at this third example, this diene is a stereoisomer of the first one. And we can see that the methyl groups in the product have a different stereochemical relationship for the third reaction relative to the first one. Those methyl groups are anti in the product for the stereoisomer of the first diene. Looking at the second reaction here in the middle, this methylene unit is the substituent of both carbons 1 and 4, and it ends up on the same side of the ring as both carbons 1 and 4. It kind of has to. So how do we describe the stereochemical relationships in dienes? Well, the two methyl groups in the first diene, they are both on the ends of the diene. So I would call them same. They're both on the ends of the diene. Because they have the same relationship, they end up syn in the product. This is true as well of the second diene. That CH2 has the same relationship. This time it's in the middle. And yes, I'm aware it's the same thing. So here, think about this one. Let's say there are two methyl groups, both pointed into the middle. I mean, obviously, that molecule would basically never occupy the S-cis conformation because of all that steric interaction. But like this is what I mean about the CH2 group, okay? It's in the middle. So these two methyl groups would have the same relationship. They're both in the middle. And the opposite of this is true for the methyl groups in that last diene. They occupy different positions. One is on the end, and then one is pointing into the middle of the diene. So they have different positions, and so they end up anti in the product. Okay, what is she talking about? Different versus same positions. So how do we think about stereochemistry in a diene? Right, here's a diene. Let's imagine rotating around the carbon 2,3 bond, going from the S trans to the reactive S cis conformation. Well, B should be on the same side of carbon 4 as is this vinyl group. So B is on the same side as the vinyl group. Same for carbon 1. B and the vinyl group are cis to one another. B and the vinyl group are cis to one another. So A and B represent the two different positions that a substituent can have on a diene. A represents the end. So the end position is pointed out of the transition state of the reaction, basically. Pointed out. I think about the reaction. Here's the transition state. Groups on the ends are pointed out of it, away from where the dienophile would approach the diene. Meanwhile, B represents the middle. So this B substituents are pointed in to the middle of the diene. They're pointed, whoa, right over here where the dienophile is approaching. So in the Diels-Alder reaction, the groups on the ends, the A's, they will end up on the same side of the cyclohexene product. And same with the middles, the B's, they will end up on the same side, the opposite side as the A's. Let's confirm that. In the first example, the methyl groups are on the ends, right? So they're both on the ends, so they're the same. They're both ends. And they do end up on the same face of the cyclohexene product. In the third reaction, one methyl group is on the end, the other is in the middle, and they end up on different faces of the cyclohexene product. They end up anti to one another. Once you have convinced yourself of this, it's time to move on. Let's use what we've just learned to predict the products of these Diels-Alder reactions, including stereochemistry. In this first example, we notice furan as the diene. It is an aromatic molecule, but it does react in a Diels-Alder reaction. And then an alkyne as the dienophile. Well, that's exciting. And yes, alkynes can be dienophiles. Check it out. This is a quite electron poor alkyne. There are 2 electron withdrawing groups on it. Let's draw the curved arrows. Now, cyclohexene product does result. Whenever there are these cyclic dienes, they can be tricky, but you will get used to it. And when these reactions are tricky, let's just draw out a generic cyclohexene, label our carbons, and then go from there. Right, so carbons 1 and 4 should still be bonded to the oxygen from the furan. So now you can see the furan here, this 5-membered ring. But the other 4 carbons have bonded to carbons 5 and 6 to make a 6-membered ring in the Diels-Alder reaction. Now, although one of the pi bonds of the alkyne reacted, the other pi bond is intact. And then there are the 2 electron withdrawing groups. Because the oxygen occupies the middle position, it'll be on the same side as itself in the product. Well, it has to be on the same side. I'm being a bit silly. We could also draw a 3D representation of this molecule, and that would look like this. We can see the cyclohexene. In this case, cyclohexadiene, because there's an additional double bond coming from the additional double bond in the dienophile. This is a good time to point out, just notice I kept mentioning that furan lost its aromaticity when it reacts in the Diels-Alder. Just notice that this is a non-aromatic product. In the second reaction, we see the trans-dienophile, which will certainly yield these electron withdrawing groups in an anti-position in the resulting cyclohexene product. And if we wanted, we can even draw that part out right now. The diene, however, is drawn in the S-trans conformation. So let's go ahead and flip it into the S-cis conformation to facilitate proper drawing of the product. Both carbons 1 and 4 have a substituent on them. They could both form stereocenters, so we need to figure out if they have the same or different relationships. Recall what I said, that the cis-trans relationships for each individual alkene do not change. So methyl is cis to the other methyl. So there we go. On carbon 4, the methyl group is trans to everything else. So here is everything else on carbon 3. So on carbon 4, the methyl group would be trans to it. Now we know that the substituent on carbon 2 is not going to form a stereocenter, right? So just put that on there because that carbon does remain sp2 hybridized. However, carbons 1 and 4 become sp3 hybridized and can form stereocenters. We can see that both of these methyl groups are in the end position. So they're on the ends pointed out of the transition state. That's the same. Each one's on the end. They have the same relationship, which means they will be sent to one another in the product. And you may ask, should I put them up or should I put them down? It doesn't matter. If you put them down, you'll just be drawing the other enantiomer of the product. And you can convince yourself of that if you would like. We're getting better and better at predicting the products of Diels-Alder reactions. Okay, let's now explain why the stereochemical relationship in the diene, substituents being on the ends versus being on the middle, is preserved in the Diels-Alder product. We will use this diene as an example. If it reacted with ethylene under Diels-Alder conditions, it would form exclusively the syn diastereomer of the product, not the anti. We've understood that by saying that both the methyl groups both occupy the end position, so they'll be the same, both be on the same side, the same face of the cyclohexene product. And we'll try to understand that now. Now, when the dienophile approaches the diene and these two new carbon-carbon bonds are made, the groups in the middle, when the diene comes from the bottom, those groups get pushed up, and the methyl groups, the groups on the ends would get pushed down. But the point here is that the same action is occurring to both of those groups on the end. Because of this transition state, the groups that were in the middle of the diene end up on the same side of the cyclohexene, as do the groups that were on the end. They end up on the same side of the cyclohexene. This particular product is achiral, but it is worth noting that attack can occur to either the top or the bottom face of the diene. When a chiral product is formed, then this attack to the opposite face just makes the enantiomer of the product. So if the diene is attacking, the dienophile is attacking the top face, then the middle groups will get pushed down and the end groups will get pushed up. But as far as relationships go, those relationships are the same. The methyl groups, because they were both on the ends of the diene, end up on the same face, the same side of the cyclohexene. This time, it's just the top face. The middle groups, they end up on the same side, same face of the cyclohexene. This time, it's just the bottom face. Okay, attack to either face of the diene is equally as likely. When the product is chiral, these two different transition states lead to the two different enantiomers. In this case, this is an achiral product. There's a plane of symmetry, so it makes the same thing, but attack does happen to each face. However, the main point of this slide is just helping you understand how the ends of the diene end up on the same side of the cyclohexene product as do the middles of the diene, and it's just coming from this concerted transition state. We've learned quite a bit. I would say now is a good time to stop and summarize what we know about stereochemistry and the Diels-Alder reaction. In a normal electron demand Diels-Alder, a diene, usually with electron donating groups, reacts with the dienophile, typically with electron withdrawing groups. Now we did learn that the dienophile can be an alkyne. However, when it is an alkene, those carbons of the alkene will become sp3 hybridized in the product, and if there is an electron withdrawing group on either carbon, it will become a stereocenter. Similarly, if carbons 1 or 4 of the diene possess a substituent, they too might also become stereocenters. Those carbons 1 and 4 and 5 and 6, they have relationships to each other that are defined and that we must learn. We first learned that dienophile stereochemical relationships are preserved. In other words, when the cis alkene, the cis dienophile, reacts with a diene, that relationship between the two X groups is retained in the product. Cis leads to syn. Conversely, trans leads to the anti-product. For the diene, stereochemical relationships are also preserved. However, now we're thinking about ends or middles. So when the two substituents on the diene have the same relationship, they're either both on the end or they're both in the middle, that this will be slow if it's not a ring, if there's actually two separate alkyl groups. However, both ends or both middles end up with a syn relationship in the product. Conversely, when one substituent is on the end but the other is in the middle, they have different positions, then they end up anti to one another in the resulting cyclohexene product. Once you're comfortable with this summary, let's move on. We have two more big things to learn, and then we're done. As it turns out, there are two possible diastereomers for each of the following Diels-Alder reactions. Draw both products of these reactions. Really give this a shot. It's going to test what you have learned so far, which is good. You don't know what you know till you try. Let's start by drawing the curved arrows for each transformation. For the first transformation like this, where these two bonds will be made. For the second transformation, same curved arrows. It's always the same for the Diels-Alder, right? So the pi bond is made, the two sigma bonds are made. Keeping in mind what we summarized on the previous slide, in the dienophile, the electron withdrawing groups are cis for both reactions. Thus, we expect them to be syn in the product. So syn. For the diene, the methyl groups are occupying the ends of the diene, so they should be on the same side, syn to one another in the product. Okay, and it's the same thing for the second diene. The groups are the same. It's because they're the same thing, but they're in the middle. Okay, so there's group in the middle. Now, what is different about the products that I drew? What is different between this product and this product? Yeah, it's the relationship between the groups on the diene and the groups on the dienophile. And in fact, we see that two diastereomers are possible for each of these reactions, depending on the relationships between the groups on the diene with the groups on the dienophile. So these two diastereomers are represented by the groups on the diene being syn to the groups on the dienophile, or the groups from the diene being anti to the groups from the dienophile. Same for the second reaction. The group substituent on the diene, it could be syn, or it could be anti to the groups from the dienophile. Now, you might be wondering, well, why didn't we see this before? Well, we didn't see it before because I chose the examples really carefully so that we would not see it. Well, two diastereomers are possible, but one is predominant. This is the major diastereomer in the first reaction, and this is the major diastereomer in the second reaction. How in the world did I know that? How in the world can you predict that? Well, I'm using a rule, and that rule is called the endo rule. And I will just state the endo rule, and then I will explain it. So the endo rule states that the diastereomer of product with the ends of the diene on the same face as the electron withdrawing groups of the dienophile is favored. What in the world does that mean? It means that for this generic Diels-Alder reaction, this is the endo product, okay, the product that's favored that has the ends of the diene on the same face as the electron withdrawing groups from the dienophile. That is called the endo product. The endo product is favored over the exo product. The exo product has the ends, those end substituents of the diene, opposite to the electron withdrawing group. So the endo product is favored. Looking up at the previous slide, you can see the favored product in reaction number 1 has the ends of the diene syn to the electron withdrawing groups from the dienophile. So this is indeed the endo product. In the second reaction, the substituent on the diene is actually occupying the middle position. So the endo product has that middle substituent opposite to the electron withdrawing groups from the product. And in fact, the ends of the diene, those are hydrogen atoms. And those are on the same face as the nitriles. So again, the major product in that second reaction is also the endo product. All right, time out. What do you have to do? You have to memorize this. You have to memorize that when you can tell the difference between the endo and exo products of a Diels-Alder, the endo is favored. So the ends of the diene on the same face as the electron withdrawing groups of the dienophile. So now I've explained how you can remember the endo rule. I just want to show you the transition state that this comes from. I'm only going to show it attack to one face. So I'm only showing attack to the bottom face of the diene. That does not matter. attached to both faces can occur, and that will just make enantiomers of the product. But we're not concerned about enantiomers right now. We're concerned about diastereomers because one diastereomer is favored over the other. We want to explain that. So in the endo transition state, which is favored, the electron withdrawing groups are actually underneath in the transition state. And you might say, oh, that seems kind of weird that the electron withdrawing groups would be under the diene in the middle of that transition state. Yes, this has to do with solvation effects. This transition state can be more easily solvated, and most scientists, most chemists think that is the reason why this transition state is lower energy. All right, so middles get pushed up, ends get pushed down. The electron withdrawing groups are underneath, so that leads to a product that has the electron withdrawing groups on the same side as the ends. Right, endo, and the ends of the diene and the electron withdrawing groups from the dienophile are on the same face of the product. And just for good measure, I drew the enantiomer of the scheme at the top, if this were chiral. Okay, in the exo transition state, we have the electron withdrawing groups pointed out. And again, most chemists believe that this transition state is slightly higher energy than the endo because it is not solvated as well as the endo transition state. Again, metals would get pushed up, ends would go down, but this time the electron withdrawing groups would actually be coming out of the page. And they would be on the opposite side as the substituents that were on the end of the diene. Right, so this would be the exo product, and it is typically the minor product when you can actually tell the difference. And like I said, you will not have to think about the endo rule for all Diels-Alder reactions. We haven't thought about it at all until I gave you these examples. So don't panic, you can do it. Now we're going to practice. So predict the major product for each of these reactions. It is going to be the endo product. So the way that we can tell that we have to think about endo versus exo is that there is cis dienophile and there are substituents on C1 on the ends of the diene, C1 and C4. In this situation, we will need to consider the endo rule. All right, give it a shot. I have gotten this started on both of these reactions. In the first reaction, we can draw the curved arrows like this, generating a cyclohexene. Carbons 1 and 4 have methyl substituents, and we need to draw those in. We know that they're going to be syn to each other because they are both on the ends. So to each other, they're going to end up syn. Same with the electron withdrawing groups on the dienophile. They're cis, so they're going to end up syn, right? Cis. They're going to end up syn in the product. Now we just have to think about the relationship between the two sets of groups, right? We could have the methyls up and then the electron withdrawing groups down, or vice versa. So we could have the methyl groups on different face from the anhydride, or they could be on the same face as the anhydride. And we need to apply the endo rule here. So the endo rule says that the ends of the diene, which are the methyl groups, will be on the same face as the electron withdrawing groups from the dienophile. All right, so that means they're both going to be up. And I'm just going to show the hydrogens down, which implies that these groups are up. Now, in the case of the second reaction, the substituent on the diene is actually occupying the middle position. It is not occupying the ends. It's occupying the middle position. So it is going to end up opposite to the electron withdrawing groups on the dienophile, because the ends are going to end up on the same side. And what's on the end for this furan is actually hydrogen. So if hydrogen is up, then so are these ester groups. We will indicate that by putting hydrogen down. So the anhydride is up, and that makes the oxygen bridge down. Okay, so that is the endo product. The ends of the dienophile are syn to the electron withdrawing groups of the diene. So you could stop again now and summarize what you know about stereochemistry and the Diels-Alder reaction. We started this already right here, but we need to add the endo rule. So in your own words, add the endo rule to what you know about the stereochemistry of the Diels-Alder reaction. Once you've done that, we need to keep moving on here with the endo rule. There are two contexts in which we should consider the endo rule. We just looked at one of them. We're not going to look at the second one, where there's one substituent on one or both of the reactants. And unfortunately, it's not just the endo rule, stereochemistry, that we'll have to worry about in that case. We will also be concerned with regiochemistry. With that dire warning, there are two possible constitutional isomers of the product for each of these Diels-Alder reactions. Please draw both constitutional isomers that are possible. For each of these reactions, there are two possible ways that the molecules can react. They can react as shown in blue to yield this product, or the opposite end of the dienophile can react with the diene to form the product shown in purple. Be sure that you understand how those two possibilities are different. This reaction is an example of when regiochemistry is important because there's more than one possible reactive site. There's more than one possible way that this molecule can react. It turns out that one of these ways is favored, but the two different ways result in two constitutional isomers of product. It's the same for the second reaction. The diene and the dienophile can react in this orientation to form this product, or in this orientation to form the other product. So for both of these reactions, two constitutional isomers are possible, depending on how the dienophile reacts. And I will note, when applicable, I did apply the endo rule, so the end of the diene on the same face as the nitrile. And that's just going to be second nature now. Apply the endo rule for stereochemistry. And I've kept you in suspense long enough. Which products are formed? Well, this product is formed for the first reaction and this one for the second reaction. So why? Why is one product favored over another? The curved arrows look pretty much the same. Well, we have another catchy rule here. We call this the orthopara rule. I know these are not substituted benzenes, so orthopara doesn't really apply, but there's this 1-2 relationship between the two substituents here, so we can call that ortho, whereas there is a 1-3 relationship in the product not observed. We can call that meta. For the second reaction, we see the same thing. The product with a meta relationship between the two substituents is not observed, but the product with a 1-4 relationship, which we can call para, it is observed. So this is called the orthopara rule. How can we understand it rather than just blindly applying it? Well, it's related to the electron donating and electron withdrawing groups on the diene and dienophile. The nitrile is certainly an electron withdrawing group on the 2 carbons of the alkene with which it is conjugated. We can represent how the nitrile withdraws electron density from the alkene with this resonance structure. Now, this is certainly the major resonance structure. However, we can infer from the minor resonance structure that there is a partial positive charge on the carbon that is beta to the nitrile. That's because nitrile is electron withdrawing. Now, alkyl is electron donating. And I am going to actually show you this with the methoxy equivalent. We can make the same argument for methyl, but it'll be easier for me to draw resonance structures for you with methoxy, and I think that you'll like it better this way. So we know methoxy is an electron donating group just like alkyl groups. We can draw resonance structures, and we'll draw two of them. For the first one, I'll just go all the way to this resonance structure where there's a buildup of negative charge on the end of the molecule. We can draw another resonance structure as well, but it's not as important because it doesn't have a charge on one of the ends of the diene, and those are the two carbons that are reacting. So that's why this resonance structure is a bit more significant, right? The ends of the diene will react with the carbons of the dienophile. So this resonance structure informs us that the end of the diene has a partial negative charge, and that'd be the same for if this were just methyl alkyl. It's just easier to understand when we can draw resonance structures, which we can do for alkoxy. All the partial negative charge on the end of the diene will be attracted to the partial positive charge on the beta carbon of acrylonitrile, which is the name of that dienophile. These oppositely charged ends are going to attract, thus they will react in this orientation, resulting in this product, where there is a 1-2 relationship between the substituent from the diene and the substituent from the dienophile. Stereochemistry does matter, and I apply the endo rule and put them on the same face. Ends of the diene, electron withdrawing group on the same face, endo rule. And that is why we do not observe the constitutional isomer of product where the nitrile reacted from the other end, because that would not line up the partial negative charge on the diene with the partial positive charge of the dienophile. We can apply a similar method to understanding the second reaction. And I will not redraw the resonance structures for acrylonitrile, but we know the beta carbon is electron poor due to this resonance structure. Now, this time I have moved the electron donating group to carbon 2 rather than the end of the diene. And the resonance structure that's relevant here is this one, which shows that the end of the diene has a partially negative charge. So that means these two carbons are going to be attracted to one another. So when they react, they're going to react in the other orientation. We'll erase and redraw, leading to this product. These bonds are made. Okay, so again, we can see one constitutional isomer of the product is formed, and it has to do with electrostatics. So thinking about what parts of the molecule are electron rich or electron poor. So a good rule of thumb is that the constitutional isomer of product with an ortho relationship between the electron withdrawing and donating groups, or a para relationship, those constitutional isomers will be observed, not isomers with a 1-3 relationship, because in those products, the partial positives and partial negatives will not line up, and opposites attract. All right, we have a few more practice problems here. The electron donating group on the diene makes the end of the diene partially negatively charged. The alpha beta unsaturated ketone has a beta carbon with a partial positive charge. If you have forgotten that, you can always draw out the resonance structure that has a positive formal charge on the beta carbon to rationalize this. And now opposites attract, so the partial negative end of the diene attacks the partial positive end of the dienophile. Completing the Diels-Alder curved arrows leads to this product. And I did apply the endo rule to put the end of the diene on the same face as the electron withdrawing group of the dienophile. Okay, next example. So another electron donating group will make the opposite end of the diene partially negative. There's an electron withdrawing group here that makes the beta carbon partially positive. So these two carbons are going to interact in the Diels-Alder. So I'll redraw that dienophile over here. All right, so the partially negative end of the diene attacks the partially positive end of the dienophile. Complete the curved arrows. A cyclohexene does result from this reaction, but it is tricky since there was a cyclic diene. So there's that bicyclic structure, the bridge. I will go ahead and draw this out in its 3D conformation as well. Okay, here it is. I've applied the endo rule once again. The electron withdrawing group from the dienophile and the end of the diene are syn. And I lined up partial negative with partial positive. So you can see ortho. So this ortho-para rule does really help us predict the product. Okay, I have dienes on the left today, dienophiles on the right, but we do see there's an electron donating group, and it is going to make this end of the diene partially negative. Now, this is an alpha beta unsaturated aldehyde, so the beta carbon is partially positive. That means that these two atoms will interact. They will attract one another. All right, so let's apply the Diels-Alder curved arrows here. Because we started off with an alkyne, a cyclohexadiene is formed. And there is no stereochemistry here, but we do see this para relationship. It's 1,4 relationship between the electron withdrawing group on the dienophile and the electron donating group on the diene. As usual, this has been a long video, longer than intended, so we're going to quickly summarize here. The Diels-Alder reaction involves typically an electron-rich diene with an electron-poor dienophile. The 4 pi electrons of the diene react with the 2 pi electrons of the dienophile in this pericyclic reaction where the electrons move in a ring to generate a cyclohexene. The Diels-Alder can run in the forward direction or in the reverse direction. In the reverse direction, the curved arrows would look like this, breaking the bonds that were formed in the forward direction. This is a reversible reaction. We can predict the products of the Diels-Alder reaction, including stereochemistry and regiochemistry. The things to keep in mind for stereochemistry were that the stereochemistry of the dienophile is preserved in the product. Cisalkene gives the syn product, while the transalkene gives the anti-product. The Diels-Alder is a stereospecific reaction. The stereochemistry of the diene is also retained in the product. We discussed ends and middle. If both groups are on the end of the diene, then they will be syn in the product. And if one group is on the end and the other is in the middle, then those substituents will be anti on different faces in the product. And then sometimes the relationship between the stereochemistry on the diene and the dienophile matters. In other words, there are two possibilities that can be distinguished between. We applied the endo rule, which describes the observation that the substituents on the ends of the diene are syn to the electron withdrawing groups on the dienophile in the cyclohexene product. And groups in the middle will be anti to the electron withdrawing groups from the dienophile in the cyclohexene product. And the middle group will be anti because the end groups are still syn. So we can see the hydrogens are actually on the ends of this diene, and the hydrogens are what is syn to the electron withdrawing group. Okay, and then when there are constitutional isomers of product possible, relationships between the electron donating groups and electron withdrawing groups will result from electrostatic attractions. Opposites attract. And those electrostatic attractions do result in the ortho or the para relationship between the electron donating and withdrawing groups in the product. And also note, this was about regiochemistry, constitutional isomer of product, but I did have to apply the endo rule to the stereochemistry. So a bunch of stereochemistry, a little bit of electrostatics. You can review the rates on your own. That was S cis versus S trans, and really it's just time to practice.